Welcome back, students. We have talked about refraction through a few surfaces. We started with a rectangular prism, and then we said there would be a lateral shift in the way the light travels through the rectangular prism. We'll demonstrate that now. I've not done the demonstration before. I want to do a few demonstrations today before proceeding to do the rest of the lesson. So I've taken a rectangular prism here. This is a rectangular prism I have. I'm going to keep this prism on this paper, which has parallel lines anyway, to demonstrate things. Light has to, when we did the derivation, light had to travel through this and then had to come out of this, right? That's how we did it. So, I can demonstrate it through this surface, keeping it like this also, but I want the light to go through this surface and then get out of that surface, as we did in the class, in the previous videos. So, I'm keeping it like this now, okay? If I keep it like this, I want you to observe the lines through the prism, through this prism. Note that if I'm exactly vertical, okay, like when I see the camera sees the prism through the normals, you see the lines in the prism align with the lines on the page and the paper, okay. But in the moment I move either to my left or to my right, you see, notice that the lines in the prism are shifted. Notice here, okay, like it's not, doesn't continue like this line, but notice this line is slightly shifted here. Okay, so this is what I mean by. So the more I go, you see, the more the shift is. And then as I come close to the normal, you see, I can see that there is no refraction at all. Rather, like I said, the light comes through the normal. So there is no shift. There are no angles of refraction. So pretty much, see, I wanted to pay attention to this, the first few, because I am focusing on the first few lines. So notice that they're aligned because the light is exactly through the normal as seen by the camera of this phone. Okay, then the moment I shift, you see, then those lines shift to this side, and the moment I come here, you see, and then they shift to the other side. Okay, so this is the lateral shift we were talking about in the previous videos. Okay. The other lens I want to demonstrate is this bulb lens. Okay, like I have removed the top of the bulb. I've removed the filament and filled that with water. This is actually a water lens. This is not a glass lens. Okay, because the glass is very, very, very thin, and the refracted light does not travel in the second medium of glass for too long. So it's very, very, very thin, negligible distance. So this is basically a water lens. Okay, you can see that. Like my face is kind of inverted. Okay, you can see that. So this has a focal length of about 3 to 4 centimeters, and you can see that I'm kind of inverted here. Okay, my face is inverted. So if you hold it like this, then clearly you can see that it is. So in olden days, this is what we were using. When I was a kid, kids like me would not get money from parents. Parents would not even spend anything at all. Okay, it is very difficult to even get a lens. So what we used to do is something like this. We'll take a bulb, remove the top, remove the filament, then convert that into a lens, and then start showing our own movies. We'll take the film rolls, and then we'll start. We will have a mirror. Direct the light to fall on the wall, and then hold this lens and keep the the film between the mirror and this lens and make it fall on the wall, and it will have a big picture on the wall. So that used to be fun for us. So you can use this as a lens, but I want you to understand that this is actually a water lens, not a glass lens, because within the medium, the glass medium, light travels for a very small distance. It's so thin, so it doesn't travel much. It's basically a water lens. So that goes to prove that you can make a lens even out of a transparent polythene bag. Okay? Pour water into it and hold it, and then try to make some shapes. Then if the polythene bag is transparent, then light will go through it and go through the water inside and then come out on the other side, so that can be used as a lens. So it's very easy to make a lens if you think about it. And if you can somehow bring that lens maker's formula into the polythene bag, holding the surfaces properly, then you can theoretically create a lens of any focal length of your choice. Okay, so it's very easy to make lenses. Okay, this is a water lens, it's not a glass lens. I want you to understand this. The glass just gives you the shape of the lens. For this to be a glass lens, then the space inside this bulb should also have been filled with glass, but now it's filled with water. So it's basically a water lens. It's predominantly a water lens. Light, the effect of glass on the light is very small, it's negligible. Okay? But you can see that there are three mediums here: air, thin glass, and then water, where light travels for a much longer distance, and then thin glass again, and air. So water, glass, and air. Other three mediums are used, but this is basically predominantly a water lens. I want you to understand that. And then the third thing I want to talk about is prism, triangular prism. Okay, we'll derive an expression for this. Clearly, as I said, you can make a water lens, and there's a glass lens also you can make with a bulb. Likewise, you can make a triangular prism with water also, and with this is a glass triangular prism. Assuming that you have a polythene bag which you keep in the form of a triangular prism, then you can pour water into it, and if everything works fine, then you can even have a water triangular prism. So the refractive indices would be different for a glass triangular prism and a water triangular prism. So I want to tell you how light refracts in this glass the triangular prism. Okay, so this is the side you are going to see. Okay, this is the side you are going to see. I'm going to keep my finger here. You can see that my finger is here. See, this is where the object is. Okay, but notice as I move here, you will be able to see this. Okay, look at my finger, where the finger is. Okay. You see, the finger is actually here. This is the finger, actually here. But then you can see the light that is coming out of this, okay, is not same place. It's refracted. Okay, there is a slight deviation. Instead of this, then you get this. So there is a deviation in the ray. You can see that. Okay, this is where the object is, but this is where you see the image. You see. Okay, so this is the object, but then you don't see the object, the image there. But this is where you see it. So light is refracting through this prism. So we will work on the mathematics of it now. Okay, now let's take a triangular prism and derive an expression for its refractive index. And in the process we'll also come across what is called as the angle of deviation. So this is a triangular prism, okay, and you can see that it's in the shape of a triangle and it has three angles. So the prism that we have now is a it has an equilateral triangle. Okay? It doesn't have to be the case. It can even be an isosceles triangle. In that case, you'll have two equal angles, and one of the angles will not be the same as the other two. Okay, so the angle which is not the same as the other two is what would be called as the angle of the prism. So I have, this is this was a general case. So I have a triangular prism here. Okay, so I call this as A, which is the angle of the prism. This is the angle which may not be equal to the other two angles. Okay, so this is the prism now. Suppose I have a ray that hits this prism like this. Okay, so this is my incident ray, it hits the prism like that. And clearly, so you have one medium here, another medium, and then the first medium here actually. So what happens is that this will undergo the law of refraction. So I have to draw a normal to this side, right? So this would be my normal to this side. So this is the incident angle, I. And this will get refracted and it will travel in this medium like this. Okay, so I have an angle of refraction, call this as R1 now. So now it goes and hits the other side, the interface between this medium and that medium. So again, it will undergo the law of refraction. So we have to obey that law. So I need to draw a normal to the surface. With this surface, the normal could be something like this. So, and this is actually the angle of incidence for this ray, right? I will call this as R2, okay? Because it's inside, I will just call that as R2, even though that's the incident angle. The angle between the normal and then the incident ray. This is R1 and that is R2. Now, what happens is that this ray, instead of going straight, now it will bend away from the normal because we're going from a denser medium to a rarer medium. Here, this ray, if this prism was not there, what would this have done? This ray would have continued in this path. Okay, it would have continued in that path. But notice, you have got a prism here, so it bends towards the normal and it travels in the second medium and so goes and hits this surface, and here it will obey the law of refraction, and if this interface was not there, this would have gone like this and gone like that, but now because of this it's going to refract, it will go away from the normal and it will go like this. Okay. So the angle between this normal and then the emerging ray is called as the emergent angle E. Okay. Again, this is also an angle of refraction, but I'll call this as emergent angle. There are two angles of refraction, right? There is one angle here and there is another angle here, but then this angle I am going to call as the emergent angle. Okay. This incident angle and its emergent angle. Okay. So R1 and R2 are, R1 is angle of refraction for the first surface, and then R2 is the angle of incidence for the second surface. Okay. Let me say that this is hitting here. This point is P, and then this point, let's say, where the normals intersect, that's Q, and then okay, and I'll call this as R. Okay. So this point is P, this point is Q, this one is Q, and this is R. So R is where this ray hits the other surface and gets refracted from there. So this is the setup now. So again, I have A and then P, Q, R. These are the important points on the prism. But notice here, if this prism was not there, this ray would have gone straight. Because the prism is here, now this ray seems to be bent, like my finger. Remember, my finger was here actually, okay, but then you saw the finger here, right? So there was this shift in the way you saw, right? Because it was like this. I don't know if you're getting it properly because the camera is opposite to me. Hopefully you're able to see it, because my finger is here, and when my finger is here, then you will see the image somewhere here. So instead of the ray coming to you straight, then it is bent and then it's reaching you. So that is that's what I mean by it. The ray should come there, but then it's coming like this to you. So like this angle, the angle between the original ray and then the emerging ray, that is called as delta, which is the angle of deviation. Let me just name the angles. A is the angle of the prism. Okay. And E was the emergent angle. And delta is the angle of deviation. So, if the prism was not there, the ray would have gone straight. Because there is this prism, the ray appears to be bent. Okay, so, not appears to be, the ray is actually bent, the object appears to be somewhere else. The object is here, but then as you see from here, the object would be, you would see the object to be here. Okay. But the object is actually here. So that's how you will see it. So that's what these are three important angles now. Okay. Now let's do some manipulations. I want you to consider the quadrilateral APQR. Okay. I'll call this as maybe this angle I choose, right? So I'll say this is N. So PQNR. So the quadrilateral PQNR is to be considered now. Okay. So what's the total angle in the quadrilateral? It should be 360. Like whether you take a square or a rectangle or a parallelogram, whatever be the shape of a quadrilateral, the total angle inside, okay, we sum all these angles, it should be 360 degrees. Why? I mean, I can divide them into two parts now. I have two triangles, so this triangle and this triangle, and you know sum of the angles of this triangle is 180 and this triangle is 180. So if you sum all the angles, then it should be 360 degrees. I know that. So the sum of the angles, all the angles, must be 360. Okay. But notice here. So what is this angle? The angle, what is this angle? The angle at P. This one. This must be 90. It's a normal, right? The normal to the surface. And what about this angle? R. This must also be 90. So this is 90, this is 90, and this is also 90, which means that this plus this, the angle A and here, this angle Q, the angle Q, they must be equal to 180. Because you know this, right? Angle, I'll call this angle P plus angle Q plus angle R plus angle N, or I'll call this angle A. Okay. Angle A. Maybe just keep it as A. PQAR should be fine, right? PQAR. PQAR. Let's not use that. PQAR. So the sum of all these four angles is equal to 360 degrees. 360 degrees. And I know that P is 90, and then this is normal, right? The angle between the normal and then the surface. and also odd is 90. So this is 90, this is 90. So that should give me Q plus A must be equal to 180 degrees. This is 90, this is 90. So this must be equal to 180. So which means that angle A must be equal to 180 minus angle Q. So angle of the prism is equal to 180 minus Q. A and Q must be equal to 180. So A must be equal to 180 minus Q. Fine. So now I want you to consider this triangle PQR. Take triangle PQR. PQR. If you take triangle PQR, what am I going to get? So the angle, this angle, which is R1, and this angle R2, then plus Q, right? Angle R1 plus angle R2 plus angle Q must be equal to 180 because it's a triangle, right? So, which means that angle R1 plus angle R2 must be equal to 180 minus Q, angle Q. So, this is my equation 1 and this is my equation 2. You can see that 1 is equal to 2. You can see that 1 is equal to 2, which means that angle A is equal to angle R1 plus angle R2. From now on, I am going to drop this angle sign. I will just simply say A is equal to R1 plus R2. So that is one good equation I got. So the angle of the prism will be equal to R1 plus R2. Okay? But then R1 will be dependent on I. Correct? Okay. If I increases, then R1 will also increase. If I increases, R1 will increase. If R1 increases, note here, R1 increases, and then Q is always a constant. Why? Because Q is always 180 minus A. Q is going to be 180 minus A. So it's a constant. R1 can change based on I. If I increases, R1 will also increase. Why? Because the sin I by sin R must be a constant. The refractive index of this medium must remain the same. So if I increases, R1 should also increase. Then Q will remain constant. But R1 plus R2 and Q should always be equal to 180 degrees. Right? As you saw here. So if R1 increases, since Q remains constant, R2 must reduce. If R1 reduces, since Q remains a constant, because Q is always 180 minus A from here. So R2 must increase. If this increases, this should reduce. If this decreases, this must increase. Okay, so now let's come to the other side. Suppose if R2 is decreasing, let's put it this way. If I increases, R1 will increase, because we know this. What do we know? We know that mu is equal to sin I by sin R. I increases, R should also increase. So I increases, R1 increases, R1 increases, so R2 must decrease. If R2 decreases, then E, the emergent angle, should also decrease. Why? Same thing. Now it should be equal to sin I by sin R. In that case, sin R2 divided by sin E, which will be 1 by mu. So that should remain a constant, right? So effectively, what happens is, if I increases, E decreases. If I decreases, E increases. Okay? And there would be some angle, okay, there is some angle for which I and E would be the same, correct? Because if I increases, this decreases. So if I decreases, this increases. So then there will be some angle I must be equal to E. Okay? Let's see now. And before we proceed, let us focus on this delta. Okay, that's the angle of deviation. That is the angle between the incident ray and then the emergent ray. Okay, so that is the angle of deviation. Let's see what happens to this delta. So what is this delta? So this is a straight line, and I'll call this as say theta. Okay, this angle is going to be theta. So if we take the straight line, then delta plus theta, or if we take the straight line, right? Okay, let's see. This I'll call this as I. Okay, I, straight line I. So delta plus theta must be equal to 180 degrees. So we'll keep it there. Now let me take the triangle. Okay, maybe I will call this as N. This point I can call this as N, right? This point N. Let me take the triangle. In triangle PNR. P, N and this R. So that gives me this angle plus theta must be equal to 180 degrees. But what is this angle? What is this angle? I'll use a different color now. I want this angle and this angle plus theta must be equal to 180. But what is that angle? Look here. So you have a line, a straight line going like that, and there's a normal. So what is this angle basically? I'll use this color now. What is this angle? This angle? This angle must be equal to I. You see, it's like this. Like that, right? So if this is I and this must be I. This must be I. But what I want is this angle. So that angle will be I minus R1. Yeah? This I minus R1 will give me that angle. Okay? So that is going to be I minus R1, this angle plus this angle. So if this is E, then this must also be E. Right? If this is E, then this must also be E. This must be E again. Okay. This is I and this is E. So that would be, so I want this red angle. That would be E minus R2. This is equal to plus E minus R2. Okay. Plus this angle theta. This angle theta must be equal to 180 degrees. Okay. So what have we got here? This is my expression 3. And this is my expression 4. Delta plus theta is 180 degrees. I got some quantity plus theta is equal to 180 degrees. So then this delta must be equal to this. So then my delta must be equal to, I'll add these two, I plus E, okay, minus R1 plus R2. Then delta must be this, from 3 and 4. So from 3 and 4, that's what I get. Well, what is R1 plus R2? Look here, R1 plus R2 is actually A, the angle of the prism. So delta is equal to I plus E minus E. These angles you can measure. What is the angle of deviation? That is, you can measure I, small I, you can also measure E. Then you also know the angle of the prism. You know these three quantities. So from those three quantities, you can figure out what your angle of deviation is. You can figure this out. Okay? I want you to understand this first. Okay. So delta is equal to I plus E minus A. The angle of deviation, the angle between the original ray and then the emergent ray. Okay, the angle of deviation is actually I plus E minus A. So the conclusions are these. 1, A is equal to R1 plus R2, and delta, the angle of deviation, is equal to I plus E minus E. These are the two things that we figured out. So from this picture, we can very easily make out that instead of this being the incident ray, suppose I reverse it. Suppose I send the ray, in this direction. Suppose instead of keeping the object here, if I keep the object here, then what will happen is the light ray that goes like this will get refracted and then it will come back like this. Okay. So there's a symmetry that is always there in optics. So if I change the, in the lens also, you may have known. If I change the U and V, then my U will become V and V will become U. Okay, suppose I keep the object at one point and then this is a place where I get the image. I have a lens here. And if I keep the object at the image point, then the new image will be the previous object point. So this retracing will take place as far as light is concerned. Okay. So likewise, for this object which is kept here, if we take this ray, then that ray goes like this, emerges like that. And if I take this as the incident ray, then this will become the emergent ray. So this retracing will always happen in light. That's again from the law of refraction. Okay, if we were to draw a graph of the angle of deviation, delta, and then the angle of incidence, I. Why? Because I can change this angle, right? I can always change the angle. I can bring it closer to the normal, and I can take it away from the normal, so I can change the angle of incidence. So I've just told you that if this is more and this will be less, we just said that. Okay, E will be less. You can very easily see that. I explained it to you. If I is more, R will be more, R1 will be more. If R1 is going to be more, then R2 will be less, and if R2 is less, E will be less. So if I is more, then E will be less. And if I is less, E will be more. So then you see, it is like there is this kind of a relationship. If the I is more, then E will be less. And if you bring I down, then E will increase, and then if there is an angle at which I must be equal to E. And then if I bring I below the triangle, then E will be greater, right? So then what happens is that I get a graph like this. Okay. So if I increase I, E will be less. Then this will remain a constant. Okay. Then I get a pretty value for this. Then Then there is at one point, there is one eye for which this I will be equal to E. Okay, so there is, then at that point, at that angle, I will have the minimum deviation. Okay. So it's like this. More, it's like that, and if you bring it closer and closer and closer, it's like this. Okay, the refracted ray, it's like this, right? Okay, right now. So if you bring it closer and closer and closer, then it will become, this will become, it's like this. So it will come like that. So the angle of deviation will also change from here, because if this becomes small and this also becomes small, meaning that this will go there, right? This will go towards that. If this becomes, as this ray comes like this, then this ray will go like that. And then when will this ray come like this? When the incident ray goes like that, then this refracted ray will come like this, closer. And as this comes down, then this will go like that. Okay? So that is what I want you to understand the whole thing. Okay, so when will that be, when will I be equal to E? When will I be equal to E? When this ray, is parallel to the base. When the refracted ray here, when it is parallel to the base, then I will be equal to E. You can see that in the geometry very easily. Okay? When this is concealed, okay, if this is the prism, and the refracted ray is like this, then like that. If this is your I, then it will be E. Okay. So if this is like that, then this angle and this angle will be the same. R1 will be equal to R2. You can see it clearly. Okay. So when I is equal to E, what happens is D, the angle of deviation will become minimum, will go to delta M, and also R1 will be equal to R2. It's parallel. This angle is the same as this angle, so this angle must be the same as that angle. So it will be parallel. R1 is equal to R2. So what happened to A now? R1 is equal to R2 is equal to some R. Okay? Some R. So A becomes, R1 plus R2 will become 2R. A will become 2R. Well, then what will happen to delta M? Angle of minimum deviation, this part, and that is equal to, if I is equal to E, then this will become 2I minus A. Very easily. So that gives you two things. Can I represent R in terms of A and I in terms of this? So from this equation, which I will call as a used for racing, right? And this is 5 and this is 6. So from 5, R is equal to A by 2. And then from 6, and I is equal to delta M plus A by 2. Delta M plus A by 2. So R is A by 2 and I is delta M plus A by 2. So now, can I find the refractive index of this medium? It's very easy, right? So the refractive index mu 2, 1. So this is medium 1 and this is going to be medium 2. Okay? 2, 1 is going to be equal to sin I by sin R. Sin I is here, delta M plus A by 2. So divided by sin of A by 2. So I can find the refractive index of this medium just by doing this experiment. All I have to do is just keep a pin here and then get a ray, and like it's as I keep moving it from this place to the other place, then I'll find at one particular angle, this I is equal to E, and then I can draw this picture and I can get delta M for that angle. So if I get the delta M for that angle, then I can easily find mu21 from this one. When I is equal to E, then I can get delta M by drawing this picture. If this is given, if they want you to find the refractive index of this medium, then they can have a pin and then send a ray and then try to see where I see the pin. Then let me see at what angle this I is equal to this E. I can shift, I can change the angle of these the pin and find the angle at which I is going to be equal to E. And once I get I is equal to E, then just by extending it, I can find this delta M and deviation, right? The angle between the incident ray and then the emergent ray. Okay, so I can find delta M. Let me try to do it here again. So let me try to do it again. So this is my prism. So let's say this is the position, this is the point for which I get I is equal to E. So I get that. So this is what I've done. Now how do I get delta M? I just need to extend this, okay, and then I extend this, and this is the angle delta M. If I is equal to E, then just by extending these rays, then I can find the delta M. If I can measure this, then I can measure the angle very easily, delta M easily. Then put the angle here, delta M plus A anyway, the angle of the prism, divided by 2, divided by sine A by 2, that will give me the refractive index of this prism. So this is the general equation. Okay. If it's a very thin lens, what will happen? Okay, if it's a very thin lens, A will be a very small quantity. So if A is going to be a very small quantity, delta M will also be a very small quantity. In that case, I can drop the signs for very thin lenses. This is a general equation. This is for all prisms. But for very thin prisms, not lenses, very thin prisms, A is small and delta M will also be small. So I can drop the sign, so I will get mu21 is equal to delta M plus A by 2, my A by 2, 2 will cancel. And then if I rearrange things, mu21 to A is equal to delta M plus A. Okay, so I can very easily do the rest. What is my delta M? So delta M can be written as if you bring A, then A into mu21 minus A is my delta M. Okay, and if I take this A out, so it's going to be delta M is equal to mu21 minus 1 into A. But this is for very thin prisms. But this equation is a very important equation. And this is for all prisms. Okay. So by doing an experiment like this, then I can find the refractive index of this glass. All I need to do is to find an angle I which is equal to E and just extend those lines and then find delta m. If you know delta m, I and E, then now if you know delta m, then I know the angle of the prism anyway. So from that I can find this. I need I and E to know the delta m. Okay, or I should say I, the I for which E is the same as I. Then I can find delta m. Once I know delta m, because I know the angle of the prism anyway, which I can measure straight away. Okay, I should be able to calculate the refractive index of the medium with which this prism has been made. So clearly, if it is a glass prism, then I can have one value, and if it is a water prism, then I'll have different delta m for the same A. So it's like that. Hope this is clear to you.